Hello everyone. So today group 3 will be presenting on experiment 6, which is calibration of Bourdon tube pressure gauge. These are group 3 members, SYAFIQAH, NAJLAA and myself Lakshmi. We will start our presentation with introduction. Figure 1 shows Eugene Bourdon, who invents Bourdon tube pressure gauge in 1849. The purpose of inventing Bourdon gauge is to measure pressure of fluids, either liquid or gas. It is a mechanical instrument which does not need electricity. The objectives used in this experiment is to calibrate a Bourdon tube pressure gauge and create its calibration curve, also to calculate the percentage error when comparing measured and theoretical values of pressure. There are three scopes used in this experiment. First, dead weight used is 0, 0.5, 1.0, 1.5, 2.0, and 2.5 kgs. Second, the pump oil is selected as the hydraulic fluid. And third, weight of piston that used is 1 kg. Next is theory. So this is a picture that shows structure of Bourdon gauge. Today, I will explain how a Bourdon tube works. Let's start with the basics. So, Pascal's law states that the pressure applied to a confined fluid is transmitted undiminished in all directions. When we apply pressure to the palm oil inside the Bourdon tube, the pressure spreads evenly and exerts force on the inner walls of the tube. Next, according to Hooke's law, the elastic metal of the Bourdon tube deforms or straightens out when pressure increases. This deformation is proportional to the pressure applied. This small deflection of the tube is transferred through a mechanical linkage, which amplifies it into a larger movement. This larger movement is what you see on the dial. When the pressure is released, the Bourdon tube returns to its original curved shape due to its elastic properties. Consequently, the pointer on the dial resets to zero. To find the calibration of Bourdon gauge, we have to compare measured value with theoretical value. So for measured value, it will be shown by pressure gauge pointer. As for theoretical pressure, the formula used is theoretical force divide area of piston. As for percentage error, theoretical pressure minus measured pressure divide by theoretical pressure times 100%.
So for experimental setup, for the first one we have the Bourdon pressure gauge, number 2 transparent tube, number 3 weight which is 0.5 kg, number 4 pump oil, number 5 death weight tester, and number 6 1 kg piston. For methodology, the first step is apparatus was set up as in figure 3. Next, the Bourdon pressure gauge needle was set to be exactly at 0 kPa as shown in figure 4. Then 1 kg of piston was placed onto the Bourdon tube pressure gauge in figure 5. Number 3, a bubble was removed by gently rotating the piston as shown in figure 6. Number 4, the first reading of the pressure gauge, which is P measured in kPa, was recorded after the system was stabilized. The next one, weight with a total mass M of 0.5 kg was placed on the piston as shown in figure 7, and the second reading for pressure gauge P measured was recorded after the system was stabilized. Step number 6, the weight placed on the piston will be increased by 0.5 kg as shown in figure 8. Record the reading of the pressure gauge kPa on each of the increment. Number 7, step 5 to 6 will be repeated until it reaches the maximum total mass M of 3.5 kg. Then, remove the weight by a decrement of 0.5 kg as shown in figure 9. Record the reading of pressure gauge for each decrement of 0.0 kg of mass. Number 8, repeat step 2 to 7 3 times to get the average reading, and lastly, all the data will be recorded in table 1. So next is the results. The gravitational acceleration, which is G, is 9.81 meters square over second, and the fixed area of piston A is 0.00031731 meters square. So as you can see in the table 1 is the result for our experiment for measured and theoretical pressure along with percentage error. So we make a conversion from bar to kPa, which 1 bar is equals to 100 kPa. For calculations, we calculated the average reading of measured pressure after conversion from bar to kPa for 0. kg weight added in increasing order. So the formula is just adding reading 1 to 3, and then we divide it by 3 to get the average. So we get 22.33 kPa. Same goes to 0.5 kg weight added in decreasing order. So we get the P mean is 26.67 kPa.
The first question in the discussion asking about the percentage of relative error for the theoretical and measured pressure gauge. The first step is to find the theoretical force. Table 2 showing the theoretical force of the experiment with the constant gravitational acceleration, which is 9.81 meter per second square. So that is the example calculation of the theoretical force using the formula of F equal to mg over 1000. The second step is finding its theoretical pressure. Table 3 showing the theoretical pressure of the experiment with the constant of fixed area piston, which is A equal to 0.0003171 meter square, and that is the example calculation of theoretical pressure using the formula of P equal to F over A. The third step, we can find the percentage error. Table 4 showing the percentage error for each mass using the example calculation of percentage error with formula of error equal to absolute P theoretical minus with P measured over P theoretical times with 100%. Graph 1 is tabulated using the data obtained in table 1, which is measured pressure in increasing order of weight in the unit of kPa against theoretical pressure in the unit of kPa. Using the same table 1, graph 2 is tabulated on the measured pressure in decreasing order of weight in the unit of kPa against the theoretical pressure in the unit of kPa. While graph 3 using the percentage error of increasing weight in percent against the theoretical pressure in kPa. Lastly, graph 4 is tabulated using the percentage error of decreasing weight in percentage against the theoretical pressure, which is in kPa. Graph 1 plots the measured pressure values against theoretical pressure as weight are added incrementally. The graph likely shows a linear relationship with some deviation between the measured and theoretical pressures, indicating calibration imperfection or system inaccuracies. The disparity might result from minor equipment faults, uncalibrated tools, or external disturbance like air bubbles. While graph 2 visualizes the pressure reading when weights are removed step by step. The trend should ideally mirror the increasing weight graph but may show a hysteresis, which is a lagging effect due to the elastic properties of the Bourdon tube. Graph 3 shows the percentage error between the measured and theoretical values as weight is added. Higher error at specific points indicate calibration deviation, potentially decreasing error rates as pressure stabilize. This reflects the accuracy of the gauge and highlight any nonlinear responses under incremental loading, while graph 4 shows the percentage error calculated when weights are removed incrementally plotted against the theoretical pressure values. It represents how well the Bourdon tube pressure gauge resets and measure pressure during unloading. The percentage error may vary at different points of decreasing pressure. A relatively consistent error across points would indicate good repeatability. A perfectly calibrated gauge would show a flat line at 0% error. Any deviation indicate inaccuracies in the gauge performance during pressure release. The second question in the discussion asking about the source of error and method to minimize the error. The first source of error we find out is parallax error, and the method to minimize it is to ensure that the eye is perpendicular to the reading scale of the pressure gauge. The second one is air bubbles may be present in the tube. By flushing the system before starting the experiment by tapping the tube during oil filling to dislodge the tube to avoid the air bubbles. And the third one is the friction between the piston and its housing pipe. How to minimize this error is to add a small amount of oil drop on the surface of the housing pipe as a lubricant to reduce the friction.
Discussion number 3 asks us to state the repeatability and accuracy of this experiment. So, repeatability refers to the consistency of the result when the same experiment is conducted 3 times. So, in this experiment, we repeated the experiment 3 times and the average reading was calculated to ensure the results are more accurate. For example, in the first trial for an increasing order of weight, the gauge reads 0.2 bar when a 1 kg mass is added, and in the second and third trial it reads 0.25 bar and 0.22 bar. The same applied to the decreasing order of weight. This means that the small variation in value shows that the gauge demonstrates a good repeatability, and while large deviation would indicate poor repeatability. Accuracy is referred to how closely the measured pressure matches the theoretical pressure value. So in this experiment, we compare the measured pressure taken from the average reading with the theoretical pressure. The percentage error range from 2% to 28%. For example, the first 1 kg mass added, the difference between the measured and theoretical pressure value is approximately 27%. So this difference indicates that the readings are less accurate because they deviate substantially from the theoretical pressure value, while smaller differences indicate higher accuracy. So factors that may affect accuracy could include improper calibration, human error, and the presence of bubble in the system.
The experiment tested and calibrated the Bourdon tube pressure gauge by comparing its reading with theoretical pressure values during both adding and removing weights. The results showed that the percentage error ranged from 2% to 28%, meaning that the gauge was not perfectly accurate. However, it gives similar readings when the test was repeated, showing a good consistency. The accuracy was less reliable at the higher pressure, which may have been caused by issues like air bubbles, calibration error, or small mistakes during the experiment. There was also a small lag in the gauge performance when weights were removed, called hysteresis. In conclusion, the gauge worked well for consistent measurement, but better calibration and more careful testing could improve the accuracy.
For safety precaution, number 1, make sure there is no presence of the bubble in tube as shown in figure 10. Number 2, handle the weight in figure 11 with care to prevent accidental drop which could result in foot injuries. Number 3, do not place weight on piston exceed the maximum level as it may cause equipment failure. Number 4, handle the pump oil carefully to prevent spill as it can cause slippery surfaces and pose a safety hazard. These are the 5 references that we found, which is from website, book and YouTube link.